Okay, so we are working on molecular geometry lab, right? And so what I'm
Yes.
gonna do, let me grab the lab book here. I'm not gonna work on the problems given to you in your lab book. I'll come up with similar problems, but not the
Okay.
exact same ones in the lab book. So let me find the lab right here. That way I make sure I have all the columns, and then I'll show you how to use this, the molecular geometry help handout. Okay, let's see. Yeah, the pages that I have in the lab book that I have at home is slightly different from the pages you have. Let's see, it says 26 here, page 26. Okay.
Yes, it is 26.
Oh, 26 on yours too? Okay.
Uh-huh. Yeah.
Okay, so I'm going to page 27 where we actually have the actual uh, data table, right? So
Mm-hmm.
over there, you're given a substance, so substance, and then I just write here number of valence
Valence.
electrons. I'm trying not to write too much. And then we have number of electron pairs. And this is, of course, around central atom, right?
Yes.
Central atom. And then finally, I'll call this electron pair geometry. So that's the EPG, molecular geometry MG. And then this is molecular type.
Okay.
I'm running out of room. Let me see if I can make this a little smaller. But yeah, that's the idea here is you're going to be filling in this table. Okay, so that should kind of work out. Let me make this a little bit bigger right here. Okay, let's compare geometry, molecular geometry, and then finally molecular type. Okay, so the first one I'm going to write out here will be silicon with 4 hydrogens. So the biggest thing here is I'm just going to work on maybe 3 of these. That way we get practice. The biggest thing here is recognizing the process, right? Before you complete this table, you have to know how to draw the Lewis structure. So even though it's not written on here, you have to draw the Lewis structure. So silicon is in group 4, right? And in the formula I
Okay.
gave you, SiH4, we only have one silicon. So that's going to be 4 right here.
Yes.
And then we
Hydrogen.
have hydrogens, which we have 4 in the formula.
So
And
that's four.
each hydrogen contributes 1 valence electron. So we have a total of 4. So when you add these two, we end up with a total of 8 valence electrons. So I'm going to write here 8 valence electrons. Okay.
Mhm.
And then we're talking about drawing the Lewis structure. So I'm going to use the same space I have down here to answer all the questions. Okay. Since we have 8 electrons to work with, silicon will be in the center because we only have one silicon and 4 hydrogens. And then the 4 hydrogens will surround the silicon. And you have 8 electrons to work with. The Lewis rules says form single bonds between the central atom and the surrounding atom using 2 electrons each time. So we have 8 electrons to work with. I'll use the 2 electrons to form a single bond here, single bond here, single bond here, single bond here. I have to keep track of the electrons I'm using, right? So it just so
Mhm.
happens that I'm looking at this right here. I've used all 8 electrons in forming 4 bonds, right? Okay.
Yes.
So when I see this, that means that I have one group here, 2 groups here, 3 groups here, 4 groups here. So over here, I'm going to write I have 4 electron pairs around my central atom, with my central atom being silicon. Okay. In the
Okay.
electron pair geometry, I have this help document right here. So I have to scroll down to find. Oh, this is not scrolling. This is what is it doing? Let me scroll down here to find the 4 electron group section. So you see there it is, peach color. There are 3 rows that go with the 4 electron groups, and we have 3 examples here. So I want to find from the 3 options we have. I actually gave you guys some Lewis structures to help you out so you can visually compare your Lewis structure with one of the three possible Lewis structures, okay,
Okay.
to make this process easier for you. Since we have one central atom and four surrounding atoms, your structure looks more like this, but let's verify. Yes, we have four groups surrounding the central atom, right? And then let me
Mm-hmm.
see, let me scoot this out of the way.
So
How
it's
do I
a
minimize this?
tetrahedral.
Ah, I did something here. Okay, this right here says, so number of electron groups in contact with the central atom that's surrounding the central atom. The next column is number of bonded groups. After that, we have number of lone pairs. So when we're looking at this right here, we have four electron groups around the central atom, right? That's silicon. And of
Mm-hmm.
those four, all four of them are bonded groups. We don't have any lone pairs around silicon. So we are dealing with this row right here, 4, 4, 0. Four electron groups, all four are bonded groups. We have 0 lone pairs. So what else do we need? Electron pair geometry. The electron pair geometry will be tetrahedral because all four groups are bonded groups and they will form this shape around the central atom. Based on the Vesper theory, the Vesper theory tells us how the valence shell electron pairs actually repel each other to form the geometric figures. So the picture we have on the left, or the structure we have on the left, this is Lewis's version of the arrangement of the atoms in the molecule. The picture we have on the right, or the model we have on the right, this is Vesper. It's actually written in Vesper, where this tells us how the electron pairs are actually arranged around the central atom. Now remember, the electron pairs are repelling each other to move us from Lewis's structure, where all the bonds are horizontal or vertical, into geometric-like structures. And this is based on the Vesper model. So here, this is where we get the tetrahedral structure. Okay, so based on us having four surrounding groups, we end up with tetrahedral geometry. And since all four groups are bonded groups and we have no lone pair, the molecular geometry or the shape is also tetrahedral. So right here, tetrahedral, and then tetrahedral here too, because the electron pair geometry in this case matches the molecular geometry. Why? We have no lone pair. The only time the names or the descriptions are different is when we do have lone pairs. Like here we have one lone pair, two lone pairs. So you're going to be using different names for the electron pair geometry and molecular geometry. But regardless of what type of groups you have, if you have four groups around the central atom, the name given to the arrangement of those four groups is tetrahedral each time. So the electron pair geometry name is constant as long as you have the same number of groups. The molecular geometry name changes if those groups are switched from bonded groups to lone pair groups. Okay? And then we have one more thing to do, which is the molecular type. In the molecular type, you have a central atom. In this case, our central atom is going to be represented by A. And A is surrounded by four surrounding groups, so that would be B, 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 right? And then you consolidate this. So we're going to end up with the central atom written first. We only have one of that, so that's implied. And then we have four surrounding atoms. So molecular type here is AB4. So this would be AB4. Oops, I didn't realize it was out of frame right there. And that's how you work on that. Okay. So let me see what other options we had here so I can make sure I can avoid that. Let's see what else we have. Let me do CSO. Okay. So CSO will be our second one. With CSO, based on what we have here, let me see. Carbon. I have one carbon in the structure, one sulfur, and one oxygen. So one of each, right? Carbon brings in 4 electrons, sulfur brings in 6 electrons, oxygen brings in 6 electrons. So we're working with 16 electrons total. Based on the Lewis rules, our central atom has to be carbon because it's the least electronegative or furthest away from fluorine. So carbon will be in the center, surrounded by sulfur and oxygen. Okay? Now, according to the Lewis rules, use 2 electrons to form single bonds between the central atom and the surrounding atom. I'm doing this twice, so minus 4 electrons, I'm left with 12 electrons, right? And I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm out of all 12 electrons. Now remember, carbon always has to obey the octet rule. Carbon is one of those elements that obeys the octet rule all the time. So you have to help carbon get to 8 electrons. In doing so, you will use the electrons from here and from here to form a double bond between the carbon and the oxygen. So this is our Lewis structure. Now everything else we answer here is based on this Lewis structure, right? So back to this. Oh, total valence electrons. I didn't really do that right there. I have to copy this over. That will be 16, right? That's what I'm working with, total valence electrons. And then once I drew my Lewis structure, how many groups do I have? This is one group, and this is the second group. Remember, when the bonds are grouped together, the emphasis is on the group. So you want to count them as they're grouped together. If it's 2 bonds grouped together as a double bond, they count as a group. If it's a single bond, it's a group. Triple bond, group. Lone pairs, 2 dots make up one group. Okay? So we have 2 groups here. I'm going to put 2 here. Now I go to this table here, and I can only read. I don't really have options because this is the only line I can look at, the only row. Now, based on what I have, you can see how my structure is very similar to this structure right here. So you can already see, right? My electron pair geometry is what I have next. That's going to be linear because the bonds and all the electron groups look like a line. Molecular geometry also, they're all bonds. They look like a line, right? So that would be linear. Molecular type. Central atom is A, surrounding atoms are B, B, and there's no lone pair in the central atom. So when I write this down, I'm going to write it as A, B, 2. And that's how we get that over here. Okay? A, B, 2. Now, if I happen to have this molecule here, I'm just kind of going off track on purpose. If I happen to have this molecule right here, this molecule will be polar, right? Because the surrounding group on the right does not match the one on the left. They didn't ask me for all that. So I'm going to leave it as that. Then let me do one that has lone pairs. Let's see. Let me see what we have here. Let me do, oops, PCl3. Okay. With PCl3, phosphorus is in, we have 1 in the formula, and chlorine, we have 3 in the formula. Phosphorus is in group 5, correct? And then chlorines, each chlorine is in group 7, so we have 21. So we're working with how many? 26 electrons. So I'm going to write here PCl3. And this is going to be 26 electrons based on what I got. Okay. Drawing the Lewis structure, I have a central atom surrounded by 3 chlorines. Okay. And from here, I'm going to draw single bonds. 1, 2, 3. That takes up 6 electrons. I'm left with 20. So, of course, you want to make sure that the outer atoms have octet first before the central atom. So you add 6 electrons in 3 pairs, right? In 3 lone pairs. So 6 electrons become 3 lone pairs around this chlorine. Same thing here, 6 electrons again, instead of 3 lone pairs. And 6 times 3 is 18. So I've used up 18 electrons. I'm left with 2. Since the surrounding atoms already have octet, now we can help the central atom get to octet by using the last 2 electrons. And we're out. Okay. You check everything else out here. Surrounding atoms have octet. Now central atom has octet. So we're going to figure out what groups we have. This is one group, two groups, three groups, and this is the fourth group. So in this case here, we are the central atom phosphorus is surrounded by four groups. So I'm going to write here four groups because remember, the lone pair counts as a group. And the single bonds each count as a group. So I have four groups, right? Now I go to my four group section again, the salmon area, and we want to see, if you look at it, our Lewis structure looks more like this, where you have a central atom surrounded by three atoms and then one lone pair. So it looks more like this, right? You can
Yeah.
use the visual I gave you guys here to kind of match your structure, or you can just go ahead and start looking here. While we have four groups, only three of those groups are bonded groups, right? So that goes with this right here. Three are bonded groups, one is a lone pair. Okay, so we truly are using this row right here. Everything we need is in the row down here. Okay, what do we need? Oh, electron pair geometry. Electron pair geometry considers all the groups regardless of what they are. So remember, this here, tetrahedral, goes with the four groups. Even if some of those groups are lone pairs, since we have four groups, the geometry will be tetrahedral. So I'm going to write here tetrahedral because electron pair geometry considers all groups present, not just the bonded groups, right? We are focusing on what is causing the groups to bend the way they do is because all the groups are repelling the other groups present. Therefore, it's causing everything to be at an angle versus being um, horizontal or vertical, right? Okay, so we have tetrahedral. When it comes to the shape, though, we only consider the remaining group, or when it comes to the shape, we only consider the bonding groups. So in this case here, think of a tripod stand. A tripod stand looks something like this. It may have something on top. Now we're looking at only the bottom part. If you remove this top part here, what is left behind? I'm removing the top part because that's where the lone pair is. This top part here. The lone pair is right here, and the lone pair, while it causes the bonds to bend, it doesn't really contribute much to the actual shape of the molecule. The shape of the molecule is formed by the remaining bonded pairs. Okay? So scientists call this remaining shape here a pyramid. Okay? So it's called trigonal pyramidal because it looks like a pyramid with a triangular base. So we'll call this trigonal. I know I wrote pyramidal there, but it's trigonal pyramidal. Either you can write pyramidal or trigonal pyramidal. Pyramidal. That's the name that describes the shape right here. And then molecular type, back to this, we have a central atom A surrounded by three groups B, 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 and it has one lone pair E. Oh, sorry, they use L here. Some books use E, some books use L. So either one works. But in this case, I guess your lab says L, right? So you're
Yeah.
going to use L right here. Okay, so to summarize that, we have A central atom, three Bs, and then one L. So that will go over here. A, B, 3, L. Okay? Let me see if I can see a picture. Because usually on campus, I will have a. Okay, that's not what I want to show. Just trying to get some belts. Let me see if I can find something here. Okay. Tetrahedral. Because I don't know if there's an actual image of this in the slides. Tetrahedral. Yeah, this shows it right here. That's what it looks like. So instead of having like a flat molecule, like the way Lewis shows it, the tetrahedral molecule looks like that. And the next thing we have is, yeah, it looks more like this or this. In our case, it looks more like this right here. And they're showing you different variations of it. Okay. So the shape looks more like a tetrahedron. And then from there, we have the shape that's trigonal pyramidal. This is what we're seeing right here, trigonal pyramidal, right here. They have it oriented sideways, but you see it right there. It looks more like a pyramid. Yeah, like this versus that. Yeah, right here. I would say this one looks a lot better. It looks more like a pyramid right here. Okay. And then of course you have bends. Now they're showing you all three right here on the bottom right. And you have
So my
bent right
question,
there.
I thought we were not doing bend and we were only doing three, focusing on three. So it would be planar, the
Oh, we are
tetrahedron.
doing bends.
We are?
We're only going to group 4. We're not doing group
Okay.
5 and 6. But there is a bend here. There's a bend here, the last one in group 4. If you have a group of 4 and 2 out of those 4 groups, so if you have a group of 4 where 2 of them are bonded groups and 2 are lone pair groups, the shape you end up having is bent. So we're not doing the 5 groups and the 6 groups in this class, but we're going all the way here. So in your class, we have 2 bents. We have a bent in the 4 groups. This is the last row, and we have a bent in the 3 groups
Okay.
right here. Yeah, so there are 2 bents. And I've been asked before, will the bends be different? Yes, because they have different bond angles. This bend here will be a lot spread out because the bond angle is 120. This bend here will be a little bit tighter. Like, I don't know how to explain. Let me see if I can draw it. Right. This bend here will be more spread out because it came from this shape right here where the bond angle was 120, right? So
Yes.
imagine removing one of these bonds to make the bent shape. So it's a lot spread out versus the other one, this bent here came from a group of 4. So you're getting rid of 2 bonds to get the bent shape. So this is a lot closer, the gap between the 2 bonds versus that one. The gap here is just 109.5, while here it's a whole 120. But they're both called bent because they look like V shapes. And scientists were trying to distinguish that from the linear. Linear is more straight like a line, and then bent is like a V shape. Yeah. So for you guys, you're only doing this paper right here, or I guess this page right here. The group of 2, the group of 3, the group of 4, and that's it. We're not doing the group of 5 and 6 for this class. Does that make sense?
Yes, it makes a lot more sense. I was having trouble with those, just those two. The other stuff I did understand, but now I get it.
Okay. Okay. Yeah. And in the book, I think the Lewis structures come in last. I put them in first. That way, if your Lewis structure matches one of these, you can use the Lewis structure to even help you figure out what the group numbers are, just in case you're messing that up, right? You don't know how to
Yeah.
count them. You match your Lewis structure to one of these examples I gave you here, and then I've done all that work for you. You just copy it from here, but while you're copying, you're figuring out how to count it, and then of course, even all the way to nonpolar and polar and bond angles, everything is provided for you.
Yes. On the polar and nonpolar, um, let me see. The difference. Can you explain that again?
Sure.
The polar is when there is a difference. I think I have
Right.
it
So
backwards.
polar
Okay.
indicates a difference, right? And so you're looking at the difference around the central atom. So there are 2 ways that we're, well, there are 2 ways where the difference can be illustrated. The first way will be, wait, can I write with this? Okay. So the first way will be different atoms. So I'm going to write here. We're looking at the atoms to see if the atoms are the same or different. If the atoms are different, then we're definitely having a polar molecule, right? And I mean the atoms around the central atom. If the atoms are
Ah,
different, right, not between the central and the, yeah, it's the ones surrounding the central atoms. Like for example, let me stick with this part here. If the atoms are different, then we have polarity because we have different abilities, right? Because in a way, if you look at this right here, this central one, this central atom, carbon, carbon is the oxygens on either side of the carbon are pulling the shared electrons towards themselves because they're more electronegative. It's not personal, it's the nature of the element. Carbon is less electronegative, so it has less access, less ability. So whatever this oxygen is doing, the other oxygen is doing also, but they have equal ability. So whatever they're doing, they're kind of canceling out the effect. So we end up with non-polar, non-difference because these atoms have the same ability on the carbon. Same thing with the chlorine, same ability on the aluminum. But here we have fluorine that is the most electronegative and nitrogen. So the two reasons, sorry, and oxygen. The two reasons why this is polar, but I'm going to focus on the atoms first. Because fluorine does not match oxygen, this is definitely polar. But the other reason is it has lone pair. When the central atom has lone pairs, it causes the molecule to be polar. This is the simplest way I can present it. And part of the reason it does that is, let's go back to this picture right here, okay? The first Lewis structure I showed you, this one here, once again, we decided this was nonpolar, right? Because the atoms have equal abilities and there are no lone pairs on the central atom. But I can fix that by changing this. Wait, where is the eraser? Let me change that. If I put a lone pair on the central atom, lone pair here, and then I have a single bond here and a single bond here. Actually, let me go ahead and place two lone pairs, right? Like that. I have now made this molecule polar. How did I do that? By placing, the rules say, since I placed the lone pairs around the central atom, these surrounding groups are very different in such a way that it makes the molecule polar. But what really causes this molecule to be polar? Because these lone pairs are present, they will actually congregate on the same side of the molecule. Not really same side, but they'll be like here. A lone pair will be up here, another one will be up here, forcing the bonds to be like this. Now you can see that in a way you don't really have a clear plane of symmetry. As this oxygen pulls the lone pairs to itself, so does this oxygen, and now you don't have any effect on the other end canceling this out. In the beginning, when we had a double bond on either end, the effect happening here was being canceled out by the effect we saw over here. So you kind of have equal and opposite to where you have no net effect, right? And we call that no net dipole. Here you do have a net dipole because the oxygen pulling the electrons on this side and this one right here actually causes an overall dipole or overall effect pointing down like this. I know I kind of went a little deep. I usually like to keep it simple and say that if you do have lone pairs, you're sort of complicating things and introducing polarity. Okay? So bottom line, if you have lone pairs around the central atom or mismatched atoms, you're introducing the difference, and the difference here will cause polarity. Okay? So atoms, and number two, I will call it lone pair, so LP. I'm trying not to write too much. Okay? So here in this third molecule here, we have two reasons why this is polar. I wrote here it has central atom, and the central atom has got lone pairs, but it's more than that. It's the lone pairs and the mismatched atoms. This one here, nonpolar, because the surrounding atoms are all alike, right? So nonpolar. This one here, polar, because even though the surrounding atoms are all alike, you have a lone pair that's significantly different from the bonded pairs. So we have polar. Same thing over here, polar. And even the part that you're not working on, I deliberately found this to just to say polar. And then this one here also for that reason, polar. And then this right here, polar. And then, well, you guys are not working on this part, so I won't even explain this part here. But the positions of the lone pair causes the lone pairs to kind of cancel each other out. That's why we have a linear molecule versus a bent molecule. So this would be nonpolar. And then this one here, nonpolar. But once again, you guys are only going to the group of 4. So you're only going to tetrahedral level, not this level down here. But you get the idea, right? Different atoms, lone pairs on the central atom, you most likely have polar.
Makes sense now. Thank you.
Okay, you're welcome. Any other questions?
No, I think I got it. Thank you so much.
Okay. Okay, you're welcome. Have a nice evening.
You too. Thank you.
Okay. Okay. You're welcome. Bye.